So hello everyone. In the last session we have started the solenoid, and let us continue our session. Basically we have derived the magnetic field due to the solenoid, and the thing is that the solenoid is a practical solenoid. It is not an ideal solenoid. So the formula which we have derived is mu naught and I divided by 2 into cos theta 1 plus minus cos theta 2, where you have to remember that theta 1 and theta 2 should be like this. The theta 1 should be like this and theta 2 should be like this. They should be taken in the same sense. That is what we have derived. So let us just see one illustration on this, then we will further continue our discussion. Let us take one example. Suppose the example is, suppose I have a solenoid. Okay, suppose I have a solenoid. I'm not drawing properly. Okay, just you treat it as a solenoid only. Suppose there is a solenoid. Okay, suppose this is some point. Okay, doesn't matter. And suppose this angle, this is my axis. Suppose this angle is 30 degree, and suppose this angle is also 30 degree. My question is that how will you write the formula? What is the magnetic field at this point? Obviously at this point, what will be the magnetic field at point P? Magnetic field at point P is equal to mu naught n I divided by 2 will be cos theta. What is the formula? Cos theta 1 minus cos theta 2. My first question is, what is theta 1 from the diagram? What is theta 1? Remember, we measure theta 1 from this point, not from this point. So what is theta 1? Theta 1 will be how much? This is 30. This is 30. Then this will be how much? 150. So theta 1 is 150 degree. What is theta 2? It is clear that theta 2 is 30 degree. Just put this value. What is the magnetic field at point P? You will get. And direction we know that is it is along the axis. If the current is like this, if suppose the current is like this, by the direction of current we can calculate the magnetic field direction. We are not interested in the direction, but interested in the value. Direction we can calculate by curl, by using the curl or by using the thumb, that we know. Okay, that is not a problem. This value will be how much? Mu naught n I divided by 2 into cos theta 1, that is 150 degree. What is a cos 150 degree? That is cos 30. Cos 30 means minus root 3 by 2. So this will be minus root 3 by 2. Minus what is cos 30? That is root 3 by 2. Just put this value and calculate how much you will get. Minus root 3 into mu naught n I divided by 2. That is what? Weber per meter square, or you can say Tesla. That is a unit of magnetic field. Okay, or Tesla. So this is how much you will get. So basically you have to, why I have taken this example, you should know how to take theta 1 and theta 2. So that is a small discussion we have did. Okay, we are very much confident with this formula. No problem. Now let us take a case. I hope till here no one have a doubt. So let us take a case. This is very important case for a exam point of view. Let us discuss about that case. Okay, and the case is, suppose if we have an infinite long solenoid, that is something called as an ideal solenoid. Because in the last class we have discussed about the practical solenoid, we haven't discussed about the ideal solenoid. So in the ideal solenoid, let me draw the cross sectional view. Okay, I'm drawing cross sectional view because that is much easier to draw. Okay, just try to understand the things. If you want to understand everything, you have to be regular in my class, then only you can understand, because my everything is going to be linked. Okay, my every lecture is going to be linked with each other. So if you are regular in my class, if you are regularly watching the video, I am giving you a guarantee that you can solve any problem from any book, any textbook, any SC Verma, everything you can solve just by following my lectures in a sequence. So basically this is a cross sectional view. This is dot, means the current is outside. Similarly, we have a cross here, means the current is inside. Okay, no problem, like this. And suppose this is my center, but here the thing is that it is going up to infinity. Okay, it is going up to infinity. That is the thing, it is going up to infinity. Okay, from minus infinity to plus infinity. So my question is that if that is the case, what is my theta 1? What will be my theta 1? Theta 1 will be how much? This will be 180. Yes or no? Are theta 1 will be 180 or not? We have did some mistake the derivation. I hope we haven't did. Let me check. This is minus sign. Oh, sorry. Last time I did this change in the theta. Okay. Sorry. Just do a small change here. Sorry, this is a mistake from my side. Okay, let me correct it, because otherwise actually that click me, because otherwise we will get a wrong option there. This should be theta 1 to theta 2, and this is also from theta 2 to theta 1. So the value should be just please do the change in the note in your notes. See, that is not wrong, but the thing is that you have to write a minus sign here, then you will get a correct value. You have to take a minus sign here also. Okay. The property of a limit, whenever you is the property of integration, whenever you change the limit, there will be one more minus sign will be there. So that is a thing. Okay, so that means in this question also you can do one change. What is a change you can do? Let me you can change this theta to this as theta 1, theta 2, this theta 1. Okay, everything will be same, only this minus sign will be gone from minus. This is minus, this will be become plus, correct? Okay, yeah. So now come to here. So theta 1 will be 180, theta 2 will be how much? 0 degree. Yes or no? Theta 2 will become 0 degree. So what is our magnetic field? Magnetic field will be mu naught Ni. That means inside the solenoid, magnetic field is constant everywhere. Constant, that is equal to how much? Mu naught Ni. And if I talk about outside, what is the outside magnetic field? B outside is equal to, here if I calculate B outside, it is 0. Here also B out is equal to 0, means outside there is no magnetic field, and inside magnetic field is there. And if the current is going from here, it is coming outside and it is going like this, means current is like this, outside to inside. So thumb is pointing in this direction, that means magnetic field will be like this, and the value is very fixed, that is mu naught Ni. That is a fixed value. Basically, if you go at the edges, let me talk about at edge. This is at some point P. Suppose this is my point P inside. Okay, this is a magnetic field point at P. Now at edge. Now I am talking about at edge. That is at point C. Let that point C is here at some edge. Okay, some edge at infinity. At infinity we have a edge now, we have an end point. Okay, so at the end point, suppose this point is at infinity at the edge. So what will my theta 2? Theta 2 at edge, what will my theta 2? First you tell me, what is my theta 2? It will be 90 degree. Okay, because it is at the edge. What I am trying to say, this is the condition. Here suppose I place it, So theta 2 will be 90 degree and theta 1 will be 180 degree. Clear? So at the edge, if you will talk about, my theta 2 will be 90 degree and theta 1 will be 180 degree. If you put this, okay, you will get the magnetic field at point C, that is equal to mu naught Ni by 2. That is also a constant. Also a constant. Clear? So basically, what we have did, we have calculated the magnetic field for all the cases. Okay. Now let us go for the conclusion and try to conclude in the last, like what we have learned. What we have, let us, because I know there is a lot of confusion going in your mind. So let me conclude. Conclusion. Conclusion is very simple. You have to remember this slide only. See, there are the two types of solenoids are there for you. One is ideal solenoid. 99% of cases you will get this ideal solenoid. Okay. One is ideal solenoid. 99% of cases you will get this one. 90%. That is ideal solenoid. In ideal solenoid, what is the case? Basically, there are the two cases are there in this case. We have a two cases. When we call this as an ideal, basically what I am trying to say, this is, suppose this is your solenoid. Okay, suppose this is your solenoid. There are the two. This is your length L and this is your radius R. Suppose I am talking about case 1. Case 1 means if my L is very greater than what? R, then it will act as a ideal solenoid. It is a ideal solenoid. Solenoid. Ideal solenoid. It will act as a ideal solenoid. Clear? It will act as a ideal solenoid. Clear? In this case, what will be how the field will be? The field will be like this. Okay, the field will be like this. Sorry. If I draw the fields, the field will be like this. Okay, the field will be like this. Clear? Similarly, case 2. Another case 2. What is case 2? Take the same solenoid. But the thing is that it is going up to infinity. It is going up to from plus infinity to minus infinity. So here the L is 10 to infinity. In this case, it is also an ideal solenoid. Remember this. It is also an ideal. It is also an ideal solenoid. Clear? And in this case, if I want to draw the field, it will be completely like this. You can see the difference. What is the difference we are getting? You can see the difference clearly. Okay, that is a difference. It is not that much proper. Let me draw it very properly. Will be straight. Okay, like this. Inside it will be straight like this. So for both these two cases, always remember, if suppose there is some point, there will be two cases. You will get a point P, a point at the edge, that is C, and then outside point, that is point A. So remember, for this magnetic field at point P will be how much? That is mu naught Ni. Magnetic field at point C is how much? Mu naught Ni by 2. and magnetic field at outside, that is point A, will be 0. This is the formula for the magnetic field, you have to remember. And if you draw the graph, if you draw the graph for this, let me draw the graph for you. If you draw the graph, okay, you will get a graph something like this. See, at the center it is mu naught, and then at the edge it will becoming some value, and after that it become 0. Correct or not? At the edge it becoming some value, then after that center it is constant, then edge at some value, and after that it becomes 0. Only like this, then become 0. Clear? It is rotated, sorry. Let me make it straight. Okay. Or we can first do one thing. Please note down these formulas because this is very important for you. It is a type of conclusion which I have given you regarding the ideal solenoid. Okay, it is a type of conclusion which I have given you regarding the ideal solenoid, which you have to remember for your whole life. Okay, that is the only thing you have to remember for the ideal solenoid. Clear? The formulas and the clear picture of magnetic field which is there. Okay, there is a graph also, I will tell you later. Let me first tell you about the practical solenoid. Second case, we have a practical solenoid. Practical solenoid means, what do you mean by practical solenoid? There is only one case you have to remember. For a practical solenoid, just take a normal solenoid. It has a finite length L, and this radius is R, and you have to take a some point P here. Okay, some point P, and you have to find the two angles. Join it at the edges. You have to calculate, this is theta2 and this will be theta1. Simply remember, magnetic field at point P will be mu naught Ni by 2 cos theta, what, 2 minus cos theta, and magnetic field at edge. Suppose someone asks you to write the magnetic field at edge, okay, suppose at point C and then at point A. So point magnetic field at point C, how will you calculate? Mu naught Ni by 2. Tell me what will be the value of cos theta 2. Cos theta 2 will become how much? Cos theta 2 will become 90. Okay sir, this will become 0 minus some cos theta 1. Now cos theta 1 you can calculate. That is the thing. Now the second is magnetic field at A. It is non-zero, but you can't like you can just, what I am trying to say, you have to apply that formula only. Okay, so I am not writing this thing because you can apply that formula and you can calculate theta 1 and theta 2. So the general formula which is that only. Okay, I'm just it's generating one extra formula. Just you remember this general formula. This is a general formula for practical case. You have to remember. Clear? That is the thing. So if I draw the graph for this, let me draw the graph for this so that it will be more clear to you. Okay, so this is about the practical solenoid, and now let me draw the graph. So first I will draw for practical solenoid. Okay, first I will draw for then you will get a more clear idea. Then I will come to the ideal solenoid. Okay, okay. So if you draw for the practical solenoid, what you will get at the center, it is constant, some value we are getting, but as we come to the, sorry, Wait a minute. Basically, if you draw the graph, if you draw the graph, inside you will get some constant value. Okay, then it is start decreasing. It will finally come to 0, like this. Okay, it is not coming properly. Okay, first note it down. It's not coming properly. Okay, like you can draw, like it will be constant like this. It is not coming perfect. Something there like this. Okay. Like this. Clear? Plus L by 2 minus L by 2. This is about the magnetic field with X. Okay, so you draw, then you will get the graph like this, something like this. But if you see the ideal case, what is the difference in the ideal case? In ideal case, see, in the practical case, we can see that it is start decreasing as we move away from the center. Okay, as we move away from the center, it will start decreasing. But if you go for the practical case, sorry, ideal case, what you will see in the ideal case? Let us draw for the ideal case. See, everything will be same up to here. See, at center we have up to, like inside the center from minus L to plus L, it is constant. As it is coming to edges, okay, as it is coming to edge, it dropped to a some value, and when we are going away from the edge, it just becomes 0. Means from here it will directly come to 0. That is what I am trying to show. So there is a discontinuity you will get. Basically you will get some discontinuity here. So it is, that is from minus L the graph is not continuous. Okay, like this. So this value is mu naught, sorry, mu naught Ni. This is also mu naught Ni, and this value is how much? Basically, remember this thing, this is open, not close. Okay, basically this is a point of discontinuity we have, so we will draw it like this. Okay, this is a point of discontinuity we have, so we will draw it like this. Sorry for the noise. It will be mu naught Ni by, sorry, mu naught Ni by 2, and this is also mu naught Ni by 2 for this point, and rest it is 0. Externally it is 0. So like that you will draw a curve for this. You will get a curve for this. Okay, clear? So this is for the ideal. And this is for practical. Clear? Ideal and practical. I hope there is no doubt. Okay, clear? So that is about the solenoid. You have to remember this much only. Okay, whatever I have taught, that is, if you are able to understand, no problem, but you should remember how to calculate the value, and for that this slide is more than enough. You can revise this slide again and again for the formulas, and everything is there on this slide. For finding the direction, you know how to do dl cross r. That is a formula, that is a thing you have to do. Or other method I have also told you, just curl your hand in the direction of current, the thumb will give the direction of magnetic field. Just curl your hand in the direction of current, thumb will give the direction of magnetic field. That I have also told you, that also you can do. Okay, clear till here? Anyone have a doubt? Please let me know. So we have basically, if we see, we have completed the solenoid part. Okay, solenoid part we have completed. Please note it down, and if anyone have a doubt, please let me know. Note it down. Completed? Completed solenoid? Any doubt? Okay, let's proceed to the next topic. That is very important topic. Like in the electrostat, we have learned about something called as a Gauss law, correct? Similarly in the magnetism, there is another law that is called as a Ampere circuital law, which is basically used to calculate the magnetic field. All the things are same as the Gauss law. If you know about the Gauss law properly, you understand the Ampere circuital law also, because most of the things will be exactly same. Okay, that is why I have taken so much time to complete the electrostats. Okay, so let us talk about Ampere circuital law. So the first law we are going to see for the calculation of magnetic field is Ampere, on the basis of geometry, Ampere don't judge me for the spellings because I make spelling mistake. I think this is wrong. Ital. Okay. Okay, Ampere circuital law. That is a law. Now, what is the law used to state? See, in the Gauss law, we have talked about the closed surface. In Ampere circuital law, we talk about a closed loop. The first thing, this law is for closed loop. What is the difference between a closed surface and closed loop? Closed surface means, for example, we talk about cube, cuboid, okay, like that, they are the closed surface. Yes, sorry, they are the closed loop surfaces, because like cuboid, cube, okay, suppose some cone, they are the closed surface. But what is closed loop? Closed loop means, suppose a square, 2D geometries, like square, example like square, okay, like circle, circle, triangle, okay, like this. We have a closed loops are there. Okay, this law is basically used for calculation of net magnetic field at a point. If at some point I want to calculate the net magnetic field, then we use this law, correct? Now, what is the statement of this law? Suppose we have some closed surface or closed loop, and loop should have a direction. Suppose the direction is like this. I have assumed the direction like this, and it is a close. Okay, suppose the direction is like this. The currents are going, like suppose we have a current I1 here, it is inside. Suppose we have a current I2 here, it is outside. Suppose I3 current is there, which is inside. Okay, I4 current is there, which is suppose inside or suppose outside, okay, then I5 current is there, which is suppose like this, okay. These are the currents are there. Now what is the Ampere circuit law state? Ampere circuit law state that the closed integration of this loop, this mean is closed integration of b dot dl, b vector dot dl vector is equal to mu naught into I enclosed. Like we have seen in the Gauss law, we have a something called as a charge enclosed by the surface. Here we have a I enclosed by the closed loop. Okay, how much total current is inside the closed loop? Total current inside the closed loop. Closed loop. Next thing is that what is the direction of, okay, next thing if I ask you what is the direction of that dl vector, how will you find the direction of dl vector? Basically remember the dl vector direction we used to decide the direction. We can take it in clockwise sense or anti-clockwise sense. So the direction is taken by user, okay, who is going to do the calculation. They will take the direction according to that, okay. Then what you have to do, if suppose here I have to write a I enclosed, then how will you write? Okay, before that tell me one thing. What is that thing? Tell me one thing. The b we will get, sorry, the b we will get from here, it is due to the q I1 or due to I2, due to I3, due to I4, due to I5, or it is a net, it is a net magnetic field due to all the currents. That is similar to that of Gauss law. So this is a net magnetic field due to all the current, okay, not only the inside current. Okay, so for this surface if I want to write, how will you write? Let's apply for this surface, okay. For this surface I am writing close integration b dot dl vector. I have taken the dl vector direction like this, correct. So it will be equal to mu naught into I enclosed. Now what is I enclosed? Similarly there are three currents are there, I3, I4, I5, but what I will write? I3 plus I4 plus I5, which one I have to take, which one I have to write? Either I have to write I3 plus I4, sorry, which one I have to write? I3 plus I4 plus I5, I3 minus I4 minus I5, I3 plus I4 minus I5 minus I3 minus I4 plus I5, like in which of the option will be correct here? See how to find which one is positive, which one is negative. The direction in which, listen it properly, the direction in which you have taken the loop, just curl your finger in that direction. It is the thumb is pointing inside, means all the inside current will be taken as positive. So how to decide which current is positive, which current is negative? For deciding the current whether it is positive or negative, curl, remember the rule, curl the finger, curl the finger, curl the finger in direction of dl, and the direction of thumb is positive, else is negative. Simple. Now let's come here. Now curl your finger. It is coming inside, thumb is coming inside, means which current will be taken as positive? I3 and I5 is inside, so they will taken as positive, and I4 will be taken as negative. So which option will be correct? So my fifth option will be correct. So I will write as I3 plus, sorry, fifth option will be wrong. Sorry, that is not correct. I3 plus I5. So no one is correct in from this. Okay, I have written a wrong option. Basically, no one is correct. But I hope you understand the rule how to figure out which one is positive, which one is negative. So I3 should be I3 plus minus I4. That is the Ampere circuital law for this surface. Clear? Till here, anyone have a doubt? Please let me know, because this Ampere circuital law is very important, very important. You have to understand it very properly. Only the statement is important. If you understand this statement, we can solve any problem of any type. First, you have to understand the statement properly. Till here, anyone have a doubt? And obviously, as we have seen in the Gauss law, it is applicable for the symmetrical type of cases, like when we are talking about a infinite long wire like that. Similarly, here also the Ampere circuital law will be applicable for the symmetrical object, okay, which is symmetrical, for which we can easily calculate the field. Otherwise, it is not applicable for everywhere. Clear? So most of the rules will be same for the electrostats. That's what I have told in the starting of the chapter also. Okay. So those who have covered the electrostat, understand the electrostat very properly, for them it is like a cakewalk for them. Okay. So let us start our first applications of Ampere circuital law. Application of Ampere circuital law. Now, what is Ampere circuital law? State that. Let us see. Let us see the application. So first application we will start with, that is infinite long wire. Infinite long let us talk about infinite long wire. What is infinite long wire? Basically, we are taking a long wire of infinite length. We have seen that what is the magnetic field due to this. We have seen the, suppose I am taking some distance d, or let us take it as r. What is the magnetic field here? What is the magnetic field we know here? If suppose the current in this direction, we know that the magnetic field will be inside, and what is the value we know? That is mu naught I by 2 pi r. That is a formula we know, but let us derive it by the Ampere circuital law. So for deriving it by Ampere circuital law, let me draw it in this manner. I am drawing it like this. Suppose this is my wire. Okay, I am drawing like this. It is going inside. Okay, this is my wire which is going inside. So if I take a distance r and I want to find the magnetic field here, that is the case. So try to understand. I have taken this wire and I have put it like this. Okay, I have taken this wire and I have put it like this. This I am converted to this diagram. Conversion. Okay, I have did a conversion. I have taken this wire and I have put it like this inside the blackboard. So you will see the wire that is going inside, and at a distance r I want to calculate the magnetic field. So if I apply the case, you will see the magnetic field at this point will be inside like this, correct? So here the magnetic field will be inside, like downward, not inside, sorry, downward. Similarly, if I calculate here, current inside, in this case here in this direction, correct? Similarly, if I calculate here, it will be in which direction? In this direction, like this. So I can say my magnetic field will be I can say my magnetic field will be, or it is better to draw it. I can say, sir, my magnetic field will be something like this. It is not a circle. but I have tried to draw it. So I can say, sir, magnetic field will be on the circle. It will be on the circle. Correct? Any doubt? At this point, if you take, it will be in what direction? It will be in upward direction, like this. So all, and they have a constant magnitude b because the distance is same. Okay, b and b, correct? So if I, what I do, I take a small loop, circular loop, correct? And let us consider the direction is like this. Let us consider the direction is like this. If you curl, the current will be positive, no problem. So if I apply the Ampere circuital law for this, then what is the Ampere circuital law? State that closed integration of b dot dl is equal to mu naught into I enclosed. What is I enclosed? I enclosed is I only, correct? Now what is b? B is a constant because at every point it is b only. So I can take this out. DL is what? What is the angle between B and D? See, if you see at this point, suppose my B vector is what? My B vector is in this direction and DL vector is also in this direction at this point. So always at every point the angle will be 0. If you see at every point the angle you will get is 0 only. So I am not writing that thing. Okay, I hope you understand that thing. Now you have to do the integration of that DL vector. See, if you integrate that DL vector, what you will get? You will get 2 pi r. Okay, you will get 2 pi r, that is equal to mu naught into I enclosed. So what is the magnetic field we have got? Sorry, that is equal to mu naught I upon 2 pi r. That is a formula we know, yes or no? We know this formula only, yes. So that is how we can derive the magnetic field by infinite long wire using Ampere circuital law. Anyone have a doubt in this? Let me know. Doubt? Okay. Now they remember one thing I have leaved, that is toroid. We will cover after the covering all the geometries. We will cover in the last about toroid. Okay. I have not covered. Mostly people used to cover solenoid. After solenoid, they used to teach toroid, and they sometimes they used to say that toroid is exactly same as solenoid. Yeah, I will also do that, but after the Ampere circuital law, we will complete. We will then go for the toroid. Okay. So now the next case is, so this is clear, I hope. Now the next case is hollow wires. Okay. Remember in hollow wires we have two cases. Okay. One case is or we can say in hollow wire we will have a three case. When one case, suppose the radius of this is A. Radius is suppose A. So there are three cases. One is small r is less than A, small r is equal to A, and small r is greater than A. First I am writing the formula for you. In this case you will get magnetic field will be 0. Then I will tell you the reason why. Okay. At that point you will get mu naught I upon 2 pi A, correct? And at this point you will get mu naught I upon 2 pi r. Similarly we have another case, that is solid wire. How it is coming we will derive also. Suppose here also the radius is A. Okay, radius, here also the radius is A. So what you can see, first is r less than A, r is equal to A, r is greater than A. For inside I am not writing right now. If I want I can write, but let it leave like it. leave it. And now you write for this, it will be 2 pi a only. Okay, and what is for this? It is mu naught I upon 2 pi r. So if you see, only the difference is inside difference, other things are same. Okay, now what is this formula that we will write later, but let me put a question mark here. Now let us see these things first. Basically what I am going to do, I am going to derive for this, and if you understand for this, these two cases will be same, then I will go do the derivation for this only. Means what I am trying, by doing the two derivation, I will tell you the this whole 6 things. Okay, that is what I am trying to explain you. Okay, so let us start this. So first thing we are going to take is the hollow wire. Okay, let us take the hollow wire. Clear? For hollow wire, let us do the derivation. So let us let me consider a hollow wire is there. Okay, and obviously it is infinite long. We are considering it is a not look like a wire. Let me draw it properly. Okay, okay, hollow wire, and obviously if it is hollow, the current on this is suppose I, total current, and the radius is given as a. First case is what? When r is less than a. Then second case is what? When r is equal to a. And what is third case? When r is greater than a. Let us talk about first case, that is inside case. Okay, inside case, suppose at distance r, I will draw a closed loop. Suppose the direction I have taken like this. Okay, so if this is a case, for this surface I will write what? Integration of b dot dl is equal to mu sorry I enclosed. So what is the I enclosed in this? Obviously the I enclosed, there is no current inside because it is a hollow, there is no surface, so no current. So inside current will be 0. So I can say this current, this term will be 0 because I enclosed is 0. So close integration of b dot dl is equal to 0. Now we know that is b, and these things are same. B will come out, integration of dl you will do, this will also 2 pi r into b is equal to 0. So from here we get b is equal to 0, means inside magnetic field is 0, there is no magnetic field. Now before going to do this, first I will do this. Close integration of b dot dl is equal to mu naught I enclosed. Now first thing I will ask you, let us take a bigger surface because we are deriving for a bigger surface. So let us take a bigger surface, or it is better if we take a something like this. Here, okay, and suppose this distance is now r, and same I have taken the direction like this. So for this surface, if when you write for outer surface, you will write close integration of b dot dl is equal to, now what is the total charge enclosed? I, obviously the total charge enclosed inside that surface is I. Okay, so this will become b integration of dl, everything you know, because b dot dl cos 0 degree, that is you know. So b into dl integration is how much? 2 pi r is equal to mu naught I. So from here you get b vector is equal to how much? B is equal to how much? Mu naught I upon 2 pi small r. That is a magnetic field outside. So for inside, if you want to find at r equal to a, just put r equal to a in this case. Put r equal to a in equation. Okay. So what is a magnetic field? You will get mu naught I by 2 pi. Clear? So if I want to draw the graph, if I want to draw the graph, can I draw the graph also? Yes, I can draw. If you remember, it is look like a conductor. Inside there is no inside there is a no magnetic field. As it reaches r is equal to a, got some value, and then it is start decreasing. Okay, here the b is inversely proportional to r. Here the b is mu naught I upon 2 pi a. This is a graph but between b versus r. Correct? Any doubt till here? No doubt? Clear now? So that is what. So if you understand this, then this thing and this thing is same for the solid also. Okay, for the solid wire also you will get the same thing. If you do for the solid wire, you will get the same thing. Clear? Just note it down. Note it down fast. Clear? Okay. Now same thing I am going to do for the solid wire. Now let us do the same thing for the solid wire, and let us analyze for the solid wire. Now the second case is solid wire, but in solid wire we are have a result for outside and the surface. Only we have to derive for the inside. So let us draw the diagram first. So I am considering a solid wire obviously, and the current will be inside. The current will be inside like this I, and there we define something called as a current density J, which is equal to how much? I upon pi a square. Okay, radius is a, everything is given to you there. See, if I talk about r less than a, r equal to a, and r greater than a, three formulas are there. Let us first, r greater than a, I told you this will be same mu naught I upon 2 pi r. This case mu naught I upon 2 pi a. Now in this case, for r less than a, let us take a one closed surface. Clear? And suppose the distance is r and direction is like this. Okay, now for this surface, let me apply the Ampere circuital law. So I will write closed integration of b dot dl is equal to mu naught into I enclosed. What is I enclosed? Mu naught into current density into what is the area, that is pi r square. What is b? You can take, this is outside, this will be 2 pi r. So what is b you will get? It is mu naught j r divided by 2. Correct? Now put the value of j here. You will get mu naught. What is the j value? That is I upon pi r is pi a square. So you will get r upon pi 2 pi into a square. So that is a value you will get for the inside, and that is what I told here. If you, I can now fill this box or no? What is the magnetic field? This is mu naught j r by 2, or you can write it as mu naught I r divided by 2 pi into a square. These are the two formulas which you can remember. If I want to draw the graph for this also, I can draw it. Yes or no? I can draw. If I draw the graph for this, I hope it is clear to you how we are getting this. So similarly, if I want to draw the graph for this, let me just copy this graph, because almost the graph will be same. Okay, what is the change here? What is the change in the graph? If I have to do, it is a very small change. Can anyone tell me what is the change in the graph? See, initially we will have a okay. Basically, it will be how it will be something like this. Initially, it will increase, and then it will start increasing. This is at r equal to a mu naught I upon I. Correct? Any doubt till here? No doubt. So that is what about the wires. So we have seen all the cases in the wires. Now there is a no cases left for the wires, and I hope you have understand about the wires completely by the Ampere circuital law. So now in the next session we will going to start with the other geometries. We will do for infinite sheet also, and also we will solve some problem on the wires, and then we will proceed for the next topic, our next part, because I told you in the starting of the chapter there are the two parts in the chapter. First is the study of the field, and second is the study of the force. In second phase we will start doing the study of the force, how to a charge act whenever it's placed in the magnetic field. Clear? So that is our second study. Till then I hope you have enjoyed this session and you have learned a lot. So till then, take care, goodbye, and if you like it, please share it and subscribe it, and have a nice day. Thank you.